everyone. Therefore, yeah, Celine, such attending my presentation of my test topic. Today, I will present about my test topic design and implementation of bi-directional CLLC DC-DC converter. And my content include there are six parts. The first, abstract. Second, introduction. Third, problem method or simulation result. Fifth, experiment result. And lastly, conclusion. The first, abstract. This thesis yields full brick of bi-directional CLLC resonant DC-DC converter to an integrated transformer for electric vehicle application. The first harmonic approximation method for calculating value of CLLC and error analysis. A small signal method for modeling the system to analyze the dynamic performance and design the control system. And to propose the new closed-loop algorithm controller for speeding dynamic response, and also synchronous rectifies is implemented to reduce the conduction load in the switch. And the simulation software BCRDC is used to verify the performance with the result of the system time is reduced at 0.625 milliseconds in new algorithm and 1.25 milliseconds in conventional algorithm at the forward mode. And 1.25 milliseconds in new algorithm and 2.5 milliseconds in conventional algorithm at the reverse mode. 70 kHz to watt prototype EPU with the peak conversion efficiency 25.1% using the SRI forward mode, and the peak and 93.5% in forward mode and 93.1% in reverse mode without SR. And the result of the time EPU thus 50 milliseconds in the algorithm and 40 milliseconds in the conventional algorithm forward mode, and 10 milliseconds in the new algorithm and 15 milliseconds in the conventional algorithm at the reverse mode. And the next introduction, the power electric interface in an electric vehicle device. The input either IC supply, the output either the charging. The charging for there are two ways. For the battery and induction motor, and the induction motor have a two-way for charging battery and charging for battery. With the charging for battery, there are two ways. The first way will from IC supply to supply the power for battery via the DC-DC converter, and when the traction motor have a bracket stack, it will regenerate the power to for battery. And with the recharging board, battery will resupply the power for AC supply with the DC-DC converter, and also supply the power for the motor when the motor having a acceleration stack. So that's why the DC-DC converter is important in the electric system, and this thesis will focus on design and implementation bi-directional CLLC DC-DC converter with the advantage such as put up the voltage level of the battery to a high voltage, achieve zero switching for full load ramp, and provision for reverse power flow. In the traction motor, when hybrid state, it will generate it will have a additional load, and the output voltage drop when changing the load. So the motivation in this thesis will control CLLC consist of two control algorithm in the forward mode and reverse mode. And the controller implemented to ensure true more stability and reduce the cycle time. And after reading some paper and considering this method, the paper 1 using the frequency module, and it can control the CLLC and reverse CLLC with the zero switching. But the CLLC is significant big break and low zero switching in the less low. And another people using the phase modulation with the fixed frequency, and also can easily regulate output. So this people cannot control the CLLC with the wide range output. And the next, now the paper combine the passive module and regressive module. With the passive module, it apply for the low output voltage, and the passive module is applied in the medium to high power, but make the controller is method difficult and complicated. Another paper also combine the passive module and synchronous rectifier for controlling and reduce the processing load, but the cycle time is higher with the value nearly 50 milliseconds. So the thesis will propose algorithm combine the passive module and AR methods to improve the cycle time, the high efficiency. And the CLC circuits with the high side and the lower side. It also the input capacitor and the output capacitor. We also have four switch in the primary side and four switch in the secondary side. We have a CR1, CR2 with the resonant capacitor, LR1, LR2 with the resonant inductance, with magnetizing inductance, and has transformer. And the next slide we will explain about the parameters. We need to get overview of original state of CLC resonant DC-DC converter first. With the stage 1 from the T0 to T1, when at this state the F1 and F4 will turn on and power will transfer to the low in the secondary side. So that's the primary side current will turn on and read to positive, and the secondary side current also turn on and to positive. But in the stage 2 from T1 to T2, from T1 to T2, although S1 and S4 to turn on, but don't have the power supply for the low in the secondary side. So the secondary side will become to zero, and the secondary side is the primary side, and the current and the primary current will keep increase follow the current in magnetizing inductance. It's stage 3 from the T2 to T3 is the rectangle relation between X2 and X3. So that's why this state it also don't have the power supply for the low in the secondary side, and the current in the secondary side becomes to zero, and current in primary side will remain the constant value. And with stage 4 from the 3 to 4, the same with stage 1, but we change the derivative of the primary current and the secondary current. And stage 5 also the same with the stage 2, when don't have the power supply for secondary side, and it will change follow the derivative of the H2 and H3. And stage 6 is the same with stage 3 with the daytime duration of S1 and S4. And about the gate analysis, in figure 5, so the FXR equivalent circuit in the forward mode. It will describe from the CLLC circuit before, and the gain function can be derived from this FXR equivalent. And you can see the gain function, we have the K, Fn, and Q. In the figure 6, when we set the K with the fixed value and we change the Q, you can see when the Q is highest, the voltage gain is lowest, and we need to choose the Q so the voltage gain M stay in the stable zone between minimum target gain and maximum target gain. After we choose the Q, we will set with the Q, and we also change the K. So with the K highest, the voltage gain M also lowest, and we also need to choose the K so voltage gain M stay in the stable zone. And after we get overview the relationship of the K, Q, and Fm in the further slide, we will calculating the value of the CR1, LR1, LR2, CR2 to calculate this value of embedment. And in the equation 2, so the equation in the primary side and secondary side of a CR1, LR1, LR2, CR2. And in this slide, so simplify the small signal modeling With the figure A, the modified topology in the forward board. The difference with the AAR circuit will show the um, described in the nonlinear output. With the nonlinear input, it will show the relationship between the VAB, VL1, V1, and VR1, VRM, and it also show the relationship between V0, LR2, and LM. In the bottom nonlinear output, it will show the relationship between the current E0, I2 equal to current in the output resistance and the output capacitor. With the harmonic approximation, we show relationship. It is shown in the time domain, and we have a CN code. And after we bring 4, 5, and 3, and apply the small signal perturbation, we can derive the state space equation of the system, follow the equation 6. After we determine the relationship of in the fourth gen characteristic, and you get the state space equation. And in the table 3.1 show the CLC parameter with the range voltage in the upper side and the range voltage in the lower side. So the output power, the resonant frequency, and the range of the switching frequency. And from this table, we can calculating the value of the LR1, CR2, LM, CR2, and LR2. And but about the state square equation, can get translate into the Laplace domain, and the transformation can be obtained. Follow the 17, and can define the transformation follow the 19 with the real point in this. And after we know the state square equation, now the value of the L1, CR1, LM, CR2, and LR2. Next, we need to calculate about the control system design. ETCC for the maximum output voltage, the overshoot we choose lower than 0, lower than 20%, and we can calculating the damping ratio. And with the set of time, we also choose the set of time lower than 2 seconds, and we also choose the natural frequency. And in figure 9 and figure 10 show the control stream, the new algorithm in the forward mode, and conventional algorithm also in the forward mode. It also have there are two controller. The first is the controller, and the second is the current controller. After that, we generate the data frequency to control the AR controller and frequency module. And the difference between the current controller have the difference between new algorithm and conventional algorithm. This is the gain, capacitor gain in the current controller, and the current controller with the transfer function of the current will and what the with the transfer function of the current of the controller, it define the 22, and the closed loop transfer function in the forward mode can be described in the 23 with the for the controller, multiplied for current controller, multiplied for plan, and we have a controller VC1 with VC1 equal to VC multiplied for AS with the VC equal to capacitor gain plus for current plus for quantum controller multiplied current controller, and we determine the KPI. And with the A is the filter for zero and point cancelling in the test plan. And the root local equation is given by follow the 24, and we can choosing the desired position in the PD. In the figure 11 of the 0 and point of related closed loop system in the S plan, we have a triple part x equals to 0. We have the reserve location at the you put P, and we have a 0 A and C in the PI controller. And with the angle condition, we can calculating the sum of angle A and angle C, and choosing the angle A and angle C, can calculating the A and C. And with the magnitude condition, with the report P, and can calculating the KPI, follow this one. And from A and C and KPI can determine the capacitor gain control, determine the controller and the current controller. And the root locus in the new algorithm, you can see the port P, and the port A, and the port C, the port C, and you can see the root locus will increase into it nearly it have a position nearly the research precision when the gain is increased, but when the root will will run via the right hand side, so it makes the control is not stable. And the step response of CLLC closed loop with the conventional algorithm and closed loop with the new algorithm. You can see the overshoot in the new algorithm reduce compared with the conventional algorithm, and specialize the setting time. We also reduce with the setting time the step response at the conventional algorithm. So the overshoot and setting time will reduce compared with the conventional algorithm. With the Synchronous Rectification, the Synchronous Rectification is applied for reduce the conduction load with the switch, and we need to make sure um, the uh, the VGS in the secondary side will turn on, turn off. Follow we analyze this. When the S1 is S1 and S4 turn on, the switch, the current in S6 and S7 will also turn on. Turn on, but we need to determine the V S6 and S7 will also turn on at the same time. And about the turn off, we will follow on the duty cycle and the equation, and we will determine the turn off of V7 with the figure 16 to the control stream with the FR method microcontroller, and microcontroller will control the 4 switch or control the 8 switch with the master timer. And with the VS1 and 4 will turn on when the counter value starting counting, and it will stop when the counter reach the value equal to the compare by one register, and we turn off the VS1 and VS4. With the VS6 and VS6 and 7, it will turn off, it will turn on, while also the counter register starting counting, and it will turn off when the counter equal to the compare tree. With the value of compare tree, follow the disable inside, and we can simulate and implement decision rectify. And about the simulation result, you can see the current and voltage in the primary side, and we the zero for the switching condition in this switch, and the primary side current and magnetic current, it is the same we analyzed this before. And about the current and voltage in the secondary side, we have a VS1 turn on and VS7 also turn on, and VS6 and 7 will turn off follow the duty cycle when analyzed before, and it will at the same time with the current turn on and turn off. So that's why the system can control the zero switching condition, and the zero rectify method can be simulated. And with the output for this in the forward mode with the conventional algorithm and new algorithm, you can see in the figure 19 and figure 20, the output voltage is stable with the reference voltage 48, but with the same load edge, and the settle time in the new algorithm reduce compared with the conventional algorithm. And with the new algorithm in the reverse mode and the conventional in the reverse mode also, we can say the first time it will stable at the reference voltage is 20 22 222 watt 222 volt, but with the same the same power added, the settle time in the reverse mode reduce compared with in the personal in the reverse mode. And the 23 so the power flow in the bi-directional with the swan in the forward mode. In the forward mode, the power will transfer from half the side to lower side, and it will added with the 200 watt. And this side either uh, when the output voltage in the lower side is greater than 48, we change to the reverse mode. And we also have a reverse, also have the added power added in this time. And the next is the experiment result. The experiment prototype in the CLC with the host computer that is used for power switch, the oscillator scope, the CLC board with the microcontroller, and the DC short in the health side and the DC low. And the figure 25 of the communication between the host computer and controller board. The host computer will build with the Python script and it will okay with the CLC board via the UART protocol. And in the Python script, I will control the CLC board with CLC command. I will start the timer. I will start the ADC, the cutoff parameter and sampling parameter. I also start the timer with the frequency, which is equal and channel of the timer in the controller. I also set the forward mode, the open loop, and the closed loops with the PID parameter. I will start the reverse mode at the open loop and the closed loop with the PID parameter, and I will turn on the synchronous rectifier for forward mode or reverse mode. And the next is the pole flow chart in the microcontroller board, and we start to initialize the referral, and in the value control, we check the CLC command. And if the CLC command true, I will implement specification follow the CLC table before. And it's not just CLC command, I will check the PID. If PID turn on, I will start to ADC reading and PID calculating. It's not, I will keep recheck for CLC command and recheck for PID. And the internal interrupt event when having the reading data from host computer, have a reading data from ADC and conflict timer from ADC parameter. And the experimental result, let's say the waveform footprint in the board. Also implemented with the zero switching, SVDA and PGA, and also implement the SR control with the VS67 and VX114. Also implement the zero switching at the reverse mode. And figure 30, so the output for this at the forward mode, output at the forward mode, output at the forward or with the version algorithm and new algorithm. Let's say the first I will set with the 96 watt, and I will adding with the 96 watt. This will 193 watts. As you can see, when adding the low, the voltage will drop, and then it will come back to stable. And when we take take out the load, it will have overshoot and will return and keep remain the steady state. And if the zoom out in the black circle, you can see the cycle time will um, around 40 milliseconds with the conventional algorithm. But when compared with the new algorithm, the output is also stable with 96 watt and 193 watt, 32 watt, but the cycle time is reduced compared with the conventional, the 50 second. And the next is the output voltage in experimental result. You can see I also set the same load with the forward mode, and it also have a drop when we add more load, and it will have overshoot when we take a load, but um, the cycle time is 50 milliseconds. But we compare with the new algorithm with the same load, and the output is also stable at the reference voltage, and the cycle time is also reduced with the conventional algorithm 10 milliseconds. So the figure show the conversion efficiency at the forward mode and reverse mode. Because HR, you can see the efficiency around 93%. But when we have the SR, the efficiency will improve more with the SR when the peak current reach 95.1%. Conclusion and for the loss. The synchronous CLLC converter is if simulated under forward and reverse and by resonant mode, and the result of the cycle time is reduced at 0.625 milliseconds and the proposed algorithm and 1.25 milliseconds the conventional algorithm at the forward mode. And the cycle time also reduced at the reverse mode. With the 7 kHz to 200 watt per time, the peak conversion is improved when we using the SR, and the result also the time is also reduced between the new algorithm with the conventional algorithm in the powerful mode and reverse mode. And another further look, SR algorithm in the system 3.4 cannot apply for the reverse mode, and it's may because the switching frequency data resonant C, so it's made the resistance incorrect. Secondly, there's some way to enhance the efficiency, for example, using the silicon carbide power transistor to increase the efficiency up to 97.2%, and the passive module by the passive hybrid control method can adjust the cycle and switching to simultaneously. And the next slide we will show see the slide. You can see the video on our mode. And the first we will start with the process with CLLC command. We start with the forward mode. When they start, system will operation. See the output voltage and the output current. We have a better array of parameter system. You can see the output is almost stable. And the next, I will start to the synchronous rectify. When start synchronous rectify, the secondary switch will turn on, and it will enhance the efficiency. Let's say the output for this is the same, but it also turn on the secondary side of fan. And then I will the output for this is stable. And next it will stop the signal, and the power will also stop. Next slide is the reverse mode widget. And first I also start with the reverse mode. and you can see the output wise reference output wise reference at the 100 volt, and this is the output current at the harmonic side. So therefore